Chapter 14 was exploring the relationship between two quantitative variables, looking at a scatter plot, and learning about the correlation coefficient. Chapter 15 is extending on that topic, describing relationships using regression, prediction, and causation. A regression line is a straight line that describes how a response variable y changes as an explanatory variable x changes. We can do all sorts of regression analyses beyond the scope of this course that are not straight lines, but in this class we'll be dealing only with a straight line. A regression line summarizes a linear relationship between two variables. When we're doing regression, one variable is an explanatory variable and the other is a response variable. In the previous chapter, remember, we didn't care whether there was an explanatory and a response, but in regression we have an explanatory variable and a response variable. The goal of regression is to make predictions of future values. So that's the whole goal of doing regression. DNR, who has to study wildlife populations, the Department of Natural Resources, comes out and samples fish regularly. They sample fish populations. And in the field, it's actually difficult to take a fish weight because the scales are not easy to transport. And when they have battery-operated ones, the batteries die, etc. So getting a weight of a fish is not an easy thing to do. However, if they anesthetize the fish, then they can get a length fairly easily in the field with just a ruler and a flat surface. So what they'll do is they'll gather a bunch of fish, they'll gather the weights and lengths, and they'll fit a model to that scatter plot. They'll fit a line to it or a curve, and they'll use that model to make predictions for future x values. So they'll collect a new fish when they're exploring it the next year, and they'll measure the length, and they'll use that model to predict how much they think it weighs. So regression is used all the time in practice to make predictions. We're going to start with an example. My water bills at my home are variable. Not just according to the gallons of water that I use. The charges that my company charges for my drinking water vary. The rate varies from month to month. It's a little difficult to explain unless you're on this kind of billing system. I hope you are not. So anyway, it's difficult for me to predict how much my water bill is going to be from month to month. I can't just use the gallons as a good guess about what my water bill is going to be. It can fluctuate drastically. So I entered the last 23 months of my water bills into a spreadsheet and put them in a program called Minitab, and I fit a regression line to it. Notice the scatter plot on the right. On the x-axis, on the horizontal axis, I have my usage. That's the amount of gallons I used in a particular month. And on the vertical axis, I have the bill amount in dollars. So notice that right here, when I had roughly 7,000 gallons of usage, between 6,000 and 7,000 gallons of usage, my bill could be as low as $60, or it could be as high as almost $100. A lot of variability in my water bills. So let's say that I want to make a model so that I can try to get at least a general prediction of where my water bill will fall. I could fit a regression line and get the equation of the line to make predictions. We'll work with this example in a few moments. First, let's decide which line we should fit. We're going to fit something called the least squares regression line. And this is the most common regression line in software packages. If you've ever done statistics before and you used a Texas Instruments calculator to get your regression line, that's the one it fit. Some of you haven't seen this before, and that is absolutely fine. We assume that you've not seen any statistics before entering this course. The least squares regression line is the line that makes the sum of the squared vertical distances to the line as small as possible. So let's say that this is my scatter plot, and I'm going to darken in my data points in garnet here. And let's say that this line is the least squares line, or it's the regression line that we're trying to fit. The least squares line takes the vertical distance from the point down to the line, and it squares it. So it actually makes the area of a square. And for this point, my square would be small, and for this point, my square would be fairly small. It keeps moving the line until when we add the size of all three of these squares together, we make the sum of the area of all three of those squares together as small as possible. Let's picture this in an interactive display. So by clicking the link in your lecture notes, you get to this little applet. The red dots are our little made-up fake data set. The blue line is our line that we're fitting to our observations. Notice that the vertical distance from each point up or down to the line has been darkened with a dark black line. And then the gray lines extending to make the box are the squares of those vertical distances. Down here on the bottom, notice that we're squaring each of the distances and then adding them up to get our total sum of the area of the squares. We call that our sum of squares. Now, does this scatter plot look like these points have an uphill trend or a downhill trend? Looks more like a downhill trend to me. So you can actually grab the line on this display and change it. So notice when my line was up here, I started in the 35, 36 range for my sum of squares. This is my total over here on the right, on the bottom. But when I start moving my line where it should be, notice I'm getting my sums of squares smaller. And my intercept should probably be up here, and I'll change my slope of my line again by dragging it down. And notice that I can make my sum of squares pretty small. Now, in practice, if we were just trying to drag a line on a graphic illustration like this, we could be going on literally to infinity trying to make that sum of squares as small as possible. Luckily for us, computer programs will calculate that least squares line for us, using just a tiny little bit of calculus and a formula that comes from minimizing those sums of squares. After a computer package calculates the least squares line for us, we're going to learn how to find and interpret the slope of the regression line, find and interpret the value of r squared, and make predictions of the y variable while avoiding extrapolation. Let's remind ourselves what the equation of a line is. You probably learned it in this form. The equation of a line is y equals mx plus b. M is the slope of the line. That's the thing multiplied by the x. The slope is the amount by which y changes when x increases 1 unit. A slope of 0 means there's no linear relationship between x and y. A slope of 0 on a scatter plot is like this. If this is your x and your y, the slope of 0 means there's a flat line. And the reason we can say that that means there's no linear relationship between x and y is we notice that as we increase in the x direction, y does not change. So that means y doesn't depend on x. And therefore we say there's no linear relationship between x and y. Now b is the intercept of the line. The intercept is the value of y when x equals 0. Let's picture the slope of a line as a little reminder. So I'm going to draw, let's assume my slope is 2/3. If I want to picture that, I can draw a little grid with a line. Okay? And let's say that my first dot is here. That slope tells me that I should, remember this is the change in the y's over the change in the x's. So this slope is going to tell me to move over 3, 1, 2, 3, and up 2. So it literally tells me how fast the line rises. Now in regression, we're going to have a slope reported in usually a decimal form, and we're always going to imagine it as that number over 1. So we're only going to think about the x's moving in 1 unit at a time. and then how much the y's change. So let's suppose that there's a line explaining the number of ice cream cones sold and additional revenue in dollars, and it yields a slope, not a slop, of 2. And I want you to interpret this slope. Okay, so if my slope is 2, the way that we're going to look at this in regression, because when I give you slopes in regression, it's probably going to be like 2.3. It's going to have decimals on it, but we're going to imagine whole numbers just for a minute so we can get a grasp on what we're doing. We're always going to put that slope over 1. It's always legal to divide any number by 1. You're not changing it if you divide it by 1. And so the way that we want to think about that is it's the change in the y's over the change in the x's. And we said in our setup that this is explaining the number of ice cream cones sold and the additional revenue in dollars. So ice cream cones sold would be my explanatory variable, and the revenue would be my y variable, my response. So this is going to be the change in revenue over the change in ice cream sales. Now we're ready to interpret the slope like we do in regression. So I see that for every 1 additional, talking about the denominator here, ice cream sold, my y is positive, so it increases by 2. And what is my y? Revenue. Revenue increases by $2. And that's how we're going to think about the slope. Now we're going to explore the definition of r squared. Remember r, the correlation coefficient from chapter 14? R squared is literally the square of r. R squared has a completely different interpretation. R squared is the fraction of the variation in the values of y that is explained by the least squares regression of y using x as the predictor. We will do an example of that in a little bit. Now the goal of regression is to make a prediction. In order to make a prediction of a future y value at a given x, simply plug the x value into the regression equation. Some cautions and things to understand about prediction. Prediction is based on fitting a model to a set of data, so it works best when the model fits the data closely. Prediction outside the range of the available data is risky, and this is called an extrapolation and should be avoided. Now you've learned some basics of regression, and next we should do some examples.